Okay. Welcome everyone for like the 7th lecture in machine learning. So maybe before we begin the lecture, as usual, a couple of administrative things. So one thing that I want to mention is like if you go to the assignments and tutorials tab in the homepage of the course, so you could actually see self-assessment questions. Some of you asked me to update it, like I should have updated it long back. But I managed to update it with all the chapters. So you should be able to see self-assessment questions for all the 5 chapters. I would encourage you to go through and try to answer these questions after going through either the lecture, like both the lecture videos and the lecture notes. So those are the questions which would test your understanding of the subject matter. Okay, and maybe a few more things before we start. A lot of you are confused and asking me whether you can use scikit-learn for the questions in the assignment 1. You cannot use scikit-learn for questions in the assignment. The assignment clearly says in the instruction that for A1, you cannot use any external package like scikit-learn or TensorFlow or PyTorch, right? So you have to implement the algorithms from scratch by yourself. But you can use NumPy for matrix operations. So that's the only thing. And definitely you cannot use numpy.polyfit to do the polynomial regression, because the whole point of that question is for you to implement the polynomial regression by yourself. Okay, and is there anything else that I wanted to mention? Okay, so there is also another question of enter. So given that the cases are rising again, I don't think we could do a physical interim, and also there is a significant number of you who are doing the course remotely. So I'm considering few options. One of the options is to do an extra assignment instead of interim. I just want to do a quick poll to see what's the class, what is the class thinking about that. So let's do a quick poll and press A if you're okay with replacing the end term with an assignment, B if you want end term. Okay, so, well, it looks like the majority wants an assignment instead of end term. But maybe it will not be a complete replacement. Like we could do some online, like, I don't know, multi-choice exam, or I'll see if there's any way we could do a small automated exam and have like an extra assignment to complement it. Okay, so that was one thing that I wanted to pull. And okay, so there's also another thing. I spoke with some of you here and there, like even some of you during the other course that I'm teaching. So I received more feedback about the course, but I would like to get a general opinion on like how hard is this course for you? Okay, so it's nice that we have this poll option. So usually we cannot do this in a physical classroom. So can you press A if you think the course is extremely hard, B if it is in the right level? Okay. Okay, I think I will stop the poll soon. Okay, So, well, it looks like 60-40, 60 percentage of you think that it's in the right level, 40 percentage of you it's hard. Okay, I will do my best to make it accessible to everyone. Please remember that there is an anonymous Google form where you can always give your feedback. And if there is anything difficult or hard to follow, please go and mention it there, so I would know like what is difficult for you. And also, if you have suggestions for making it easier, please go and add that to the anonymous form too. And also, if you like some aspect of the course that you think should be reinforced more, or like if you think that this lecture was good and like, so this is why I liked it, please post those positive comments too. So like I need both the positive and the negative comments so that I know what technique works, what technique doesn't work. Okay. Okay, so I think that's enough. Now we will move to the lecture. Okay. Okay, so just to recap what we did in the previous lecture, we discussed about empirical risk minimization. Like we discussed about the true risk that we want to minimize and why we can never directly minimize it. So instead, we ended up using empirical risk minimization, which is the idea of minimizing the empirical risk, which is basically the risk over the training set, right? And we also discussed about like how you can decompose a loss into bias, variance, and the irreducible error. And we discussed about the bias variance trade-off, and we started with linear classification, right? So today's lecture will focus more on linear classification. So just to give you a quick recap of like what we covered in linear classification in the previous lecture. So we discussed about how there are two stages in classification, right? So in the case of classification, you have inference stage where the idea is to just learn P of Ck given X, right? And then there is a decision stage where the idea is to make a decision on what is the class that you want the prediction to be, right? By using the probabilities. So then we also discussed about three approaches or three different ways of doing classification, right? So in one extreme, we have generative models. In the case of generative models, like we care a lot about modeling P of X comma Y, right? So you model P of X comma Y, the joint distribution of the data. And once you have a good model for this, then you can actually use this to compute P of Y given X, right? Or you could also model P of X given Y and P of X, and then compute this by using the Bayes rule. We call this as generative models simply because once you have access to P of X comma Y, you could generate as many samples as you want. Okay. Then the second class of approaches were discriminative models, right? In the case of discriminative models, instead of going through this business of modeling P of X comma Y or X given Y and so on, you directly model P of Y given X. It's called discriminative model because it learns to discriminate between different classes given X. And the last approach, or the extreme, like the other extreme approach, is discriminant based model, right? So this is a simple approach where instead of trying to model the probabilities, like you will directly model some f of X. This f is a function which is like directly mapping X to Y, right? There is no probabilistic notation for this part, okay? Okay, so now these are the three different approaches. And then we also talked a bit about linear classification, right? So when I say linear classification, it means that I have a linear model with linear decision boundary, right? Like, so for example, if this is my data, let's say I have two features, x1 and x2, and I want to between the circles and crosses. Okay, so now in this case, like I could actually draw a line, and this line is going to separate the circles from the crosses, right? So we call this line as the decision boundary. Okay, and anything which is to the top of this decision boundary, right? So this is let's just call cross to be class 1 and circle to be class 2. So now this is the decision region for class 1. This is the decision region for class 2. Okay. So now we also learned that in the case of linear models, like, so if it is 2D data, you're going to learn 2 minus 1, so 1D decision boundary, which is a line. If it is a 3D data, you're going to learn your decision boundary, which is a plane, right? Like, and in the case of n-dimensional data, your decision boundaries are going to look like a hyperplane. Okay, and we also discussed that a problem can be classified as linearly separable or not linearly separable. In this case, this problem is linearly separable because I can draw a line, right? On the other hand, if I have a problem like this, where I have a bunch of circles and a bunch of cross like this, okay, so in this case, if I have to fit a decision boundary between these two, it would look something like this, right? So now this is an example for a problem which is not linearly separable. Okay, so this is where we stopped the previous lecture. Okay, so now let's continue. So before we continue the discussion, we are going to talk about like how to represent the target variable for classification. Target variable for classification. Okay, so now in the case of regression, my target variable, let's say t, belongs to a real number, right? Like it's a real number. But in the case of classification, my target belongs to a bunch of categories, right? Like, so let's say C1 to CK. For example, I could have a classification problem where I ask you to classify between dogs, cats, and let's say cows. Okay, so now in this case, there are three classes: dog, cat, and cow, and you need to choose one out of these three, right? So that's why we call it as a categorical target. Now let's start with a simple two-class problem. Okay, so when I have two-class problem, let's say my goal is to just classify an image between either a dog or a cat. Okay, so often when you have such categories, like we will convert it into numerical values so that we could use our models which deals with numbers, right? So let's, like, one standard way to do this is to say the target is equal to 1 for class dog, okay, and the target is equal to 0 for class cat. Fine. Now, instead of the target being dog comma cat, we have converted it into some numbers which are 0 comma 1. Okay, so now one way to interpret this number is you can consider t to be the probability that the class is, in this case, dog. Okay, So when I say t is equal to 1, it means it is very high chance that it is class dog. On the other hand, if the model predicts t is equal to 0, then it is very chance that it is cat, right? So which means there's a high chance that it is not a dog. So t can be interpreted as a probability that the class is the first class, right? But it is just that this probability takes extreme values. So you only have 0 or 1. You don't have the whole range in between. So values of 0 and 1. Okay. So now this is for two class problem. Now let's say I want to solve a classification problem which has more than two classes. Okay. Now here is an idea. So how about, okay, let's take some example. Let's say I have dog, cat, I don't know, plane, cow, crow, because I have 5 classes. Okay, so here's an idea. So how about I map them into 1, 2, 3, 4, and 5. So is there any issues in directly mapping these random set of classes into numbers 1 to 5? Can someone answer by raising your hand? Okay. Mohammed, can you unmute Gay?
Yes, I think there is an issue because the system will try to compare 1 to 2 and 3 and 4 and so on. So the system will take 1 like lower than 2 and so on and so forth.
Okay, so essentially what would happen is like when you're trying to make prediction for, let's say, class 3, if your system has lower value, then you're creating artificial distance between these 5, right? So since these are numbers in order, so if your system makes an error, there is more chance that, for example, it would make an error of 2.5. Like there's more chance that it is going to confuse 3 with 2 and 4 instead of 1 and 5, right? Because whenever there is a numerical error, you would be like rounding it to the closest class. So you are in some sense creating artificial distance between the classes, right? Okay, so, or in other words, in this case, like class 2 is more close to class 3 than it is close to class 5, right? Let's look at this example that we have. So then by this logic, it says cat is more close to plane than to crow, right? Like, so, well, it is, first it is very hard to say which class is close to which, right? Like it requires a lot of domain knowledge. Second of all, it is actually a very bad idea to create these artificial distances, right? Like, so you don't want to give wrong priors to the model. So ideally, you should have equal distance between all the classes so that the model is not biased towards relationship between the classes, and it learns these relationships from the data, right? So how do we do that? So one way to do that is the idea of 1 of k coding scheme. Okay, so it's also known as one hot vector. Okay, so the idea is this: when you have 5 classes, okay, so you would represent class 1 by a 1 followed by 4 zeros. Okay, and you would represent class 2 as 0, 1, 0, 0, 0, and so on. Okay, so now you have 5 vectors for 5 classes, and each vector has only one at a time. So right, like that's why it's called one hot vector, and the distance between all these 5 vectors is the same. So basically, like, you don't create these artificial distances between the classes, right? Now if you look at this interpretation, like now this this one hot vector also has some probabilistic interpretation. So essentially, the first column, right, it tells the probability for class 1. The second column tells the probability for class 2, and so on, right? So basically, each of this each tk can be interpreted as probability that the class is ck. So when I have 0, 1, 0, 0, 0, it means that the probability for class 2 is 1 and the probability for rest of the classes is 0. Okay. Okay, so what is the problem when n increases linearly in one hot representation? Well, that is not, it is linearly increasing, but it is not a serious issue. Okay, so is this clear? Okay, maybe I would take a couple of questions here before I move on. Are there any questions about representing the target?
There is one question from before, which is as follows. In the Bayes rule, you also need the prior in addition of joint distribution.
Well, if you have access to the joint distribution, then you could get any probability that you want by marginalizing the joint distribution. Okay. Okay, so there, okay. Okay, so there's a question that I didn't understand the difference between discriminative and discriminant model. In the case of discriminative model, you are essentially modeling P of the probability of Y given X. On the other hand, discriminant based models are not probabilistic. You have a scoring function which scores, okay, what is the class for this X, right? So we are going to discuss more about discriminant functions in today's lecture. Probably that would help you to clarify your doubts. Is there a better way to represent target when there are target classes that are dependent? Okay, when you have an X, when you have when you know or when you have the prior knowledge that there is a dependency between the classes, there are ways to represent this dependency, and you could start making structured predictions, which is something we will not cover in this course. Okay, so I think I will continue. Okay, so for today's lecture, we will be focusing, so we are going to discuss about all these 3 ways to do classification, but we will start with some basic discriminant based classification. Okay, so to do that, for today, we are just going to understand the properties, geometric properties of discriminant functions and the linear decision surfaces. Okay, so now what is a discriminant function? A discriminant function is something which takes an input vector X, okay, and assigns it to one of K classes. It's a function which takes X and assigns it to one of the K classes, okay. So when you have linear discriminants, which is what we are going to initially focus on, okay, then they are essentially linear models. So the decision surfaces are hyperplanes. Okay, so now we will start our discussion with 2-class scenario, and then we will move to K-class scenario. So first, let's start with 2-class scenario. I have 2 classes to classify, and let's consider a very simple linear discriminant function, which we have already learned in this course, right? So a simple linear discriminant function, which is basically y of x is equal to w transpose x plus w0. Okay, so this is the standard linear model that we have learned, where w0 is the bias and w is the weight vector. Okay. Now, how would I use this model? So one way to use this model is if whenever y of x is greater than or equal to 0, then I could call that as class 1. And whenever y of x is less than 0, then I'm going to call that as class 2. Okay. So now in this case, what is my decision boundary? My decision boundary is basically y of x is equal to 0. Whenever y of x is equal to 0, that is the line between the first class and the second class. If y of x is greater than 0, then it is class 1. If it is less than 0, it is class 2. Okay. So now we can understand the significance of this W0 now. So this W0 can actually tell you like the threshold for classification. Okay, so for example, if W0 is equal to -7, okay, so, and remember that y of x is given by W transpose x plus W0, right? So if W0 is equal to -7, then W transpose x has to be at least +7 to be classified as C1. Okay, so in some sense, the bias in the discriminant model is telling you the threshold for classification. So if it is like if W0 is -7, then you need at least +7 for W transpose X so that you can classify that as C1. Okay, so in that sense, W0 is the threshold for classification. Okay, is that clear? Okay, so now, okay, so now let's start with a situation where I have two features, x1 and x2. Okay, so when I have two features, so what would be my decision boundary? So my decision boundary is going to be a line, right? Since this is 2D, so the decision boundary is 2 minus 1, 1D, so it's a line, right? So to remind you again, if you have a 3 data, the decision boundary is a plane, and if you have ND, the decision boundary is a hyperplane. Okay, so now in this case, let's say I have my decision boundary, something like this. Okay, so this is the line for y is equal to 0. Okay, so anything above y is equal to 0. So whatever y is greater than 0, that is my region 1. Region 1 is the region of class 1. Okay, so now when y is less than 0, so that is my region for class 2. Okay, okay, so now we are going to consider two random points in the decision surface. Okay, so let's just call the first random point as XA, the second random point as XB. Okay, so consider two random points, XA and XB, both of which lie on the decision surface. Okay, so now these points lie on the decision surface, right? So now what would be the value of y of x of a? Maybe some answers in chat since it's difficult to pull here. So XA lies in the decision boundary. So what would be y of XA? Okay, so it lies in the boundary, and we know that the boundary is a place where y is 0, right? So this is going to be 0. Similarly, y of xb is also going to be 0, right? So y of xa is equal to 0. I'm just going to expand the function. It becomes W transpose xa plus W0 is equal to 0. Similarly, W transpose xb plus W0 is equal to 0, right? So I'm just going to take these two functions and write as like do a little bit of like moving around, and this is basically W transpose XA. Well, maybe I'll just do it like even though it's trivial. So plus W0 is equal to W transpose XB plus W0, right? Simply because they're both equal to 0. This cancels out. And you have W transpose XA minus XB is equal to 0. Okay. Now, this is our first interpretation of this linear discriminant function, okay, the decision boundary. So what is this? XA minus XB is the line passing through XA and XB, right? So this is the equation for this line, right? And this equation basically means that W vector is orthogonal to every vector lying within the decision surface. Okay. In some sense, if this is my decision surface, then my W vector has to be exactly orthogonal to this decision surface. Okay. And in that case, if I tell you that this is the decision surface, then you already know the direction of the W vector. So the W vector is going to be something like this. Right? So if you look, so this should be 90 degree. Okay, maybe my picture is bad, but the angle between the W vector and the decision surface has to be 90 degree. Okay. So in other words, W determines the orientation of the decision surface. Is that clear? Okay. So now that is our first observation. So the observation is, if you give me the decision surface, then this W vector is going to be orthogonal to the decision vector, or in other words, W decides my decision, like what would be the direction, orientation of my decision surface. Okay. Okay. So now next observation, maybe it's easier if I just copy this figure. Let me copy. Okay. Okay, I have my figure here. Okay, so now we know that W is orthogonal to the decision surface, right? So now the next question is, any point X dash on this decision surface that is closest to the origin can be represented as X dash is equal to alpha W for some scalar alpha. Okay, so what I'm trying to do here is I'm trying to, okay, now we know that the direction of W tells you like where the decision surface is, right? So now we are trying to understand the distance of this decision surface from the origin. Okay, to understand that, we essentially need to compute the distance from the shortest distance from here to the decision surface, which is exactly this line, right? The green line that I'm drawing. Okay, maybe to make things clearer, I'm going to erase this portion. Okay, and let's say this is my W vector. Okay, now the distance of the decision surface from the origin is given by this red line, right? Now you can see that this red line is basically some rescaling of my W vector, right? So that is exactly what I am trying to formulate here. So the X dash, which is the line from origin to the decision surface, the shortest line, the closest line, is basically some alpha times W, okay? Now we already know that X dash on the decision surface, right? So, okay, someone raised hand, Alaji.
Yes, sorry. I don't understand why we can write X dash like this.
Okay, so I want to find the vector which has shortest distance to my decision surface. Okay, so for example, you could consider this vector, or you could consider this vector, and you could consider this vector. So which has the shortest distance? So like basic geometry here, right? Like, so like the vector which has the shortest distance to this line is something which is orthogonal to this line,
Okay.
right? So in that sense, like you don't need the other lines, right? So it is just something which is alpha times the orthogonal line W.
Okay. Yes.
Okay. Okay, so isn't alpha directly related to W0? That is what we are going to derive now. So your observation is right. Okay, so X dash is on the decision surface, right? So we already know that W transpose X dash plus W0 is equal to 0, right? Now we also know that X dash is equal to alpha W. So alpha times W transpose W plus W0 is equal to 0. Now alpha is given by minus W0 by W square. Okay, so now what we care about is the distance from X dash to the origin, right? So that is the displacement of my decision surface. So that is given by this term, right? So which is basically norm of alpha W, okay, which is alpha times this, right? Now I could substitute what is alpha here. So this becomes minus W0 divided by W square W, right? So this essentially becomes minus W0 by norm of W, okay? Or in other words, W0 actually determines how far is this decision function from the origin, okay? So in some sense, we are trying to formalize the observation that we already had. Remember this observation where I said if W is equal to minus 7, then it basically means that the W transpose X has to be at least plus 7, right? So we are just trying to formalize this observation here by saying that, maybe I will write it down explicitly. So W0 determines the location of the decision function. Okay, so to remind you the first observation that we had, W determines the orientation of the decision function. Okay, so we are basically trying to understand what every parameter is trying to do in this linear discriminant model. Okay, so the parameter W that you have in W transpose X is trying to determine the orientation of the decision function, and W0 determines the location of the decision function. Okay, so now if I have to put this in the picture that we already had, then in some sense, let's say this distance, right, is given by minus W0 by non-W, right? So this is the second observation. Now, the final observation. Let's say I have a random X and I compute Y of X, okay? So now I get some value, right? So let's say the vector for that X is, let me use a different color. Let's say this is the vector. Okay, so now what would be the class for this X, the vector X? I think this I can easily poll. So we are going to do a quick poll. So what would be the class for the whatever new color vector I did, right? Like, so this vector that I have highlighted. So I'm going to launch the poll. A for class 1, B for class 2. Okay, so A for class 1, B for class 2. Okay, so I will stop the poll. Okay, majority is class 1, so which is right. So if you have pressed class 2, remember that this vector basically means the data point which is here, right? So it's above the decision boundary, so it's class 1. Okay, so now we want to understand, like, what does this, what does the magnitude of this vector mean, right? So now basically, let's consider an arbitrary point X. Okay, so which is this colored one. So this is my X. Okay, now I can actually decompose this particular vector into two vectors, right? So one which is the orthogonal projection to the decision function and this vector, right? So basically I could take this vector, which is basically the addition of these two vectors, right? So this particular vector from the origin to the decision surface, let's just call that as something like X orthogonal, okay? And you have this extra term, you add these two things to get the X, right? So one way to represent this in terms of equation is I could say that X is equal to X orthogonal plus some R times in the direction of my W, right? So this basic equation tells that the vector X that we have here, is there a highlighter? I'm not sure, but maybe I would just highlight like this. So this vector X, right, is divided in, it's basically a summation of two things. One is this vector plus you have the second vector. I don't know what that vector is, but that vector is orthogonal. So it is some R times W, because W is orthogonal to the decision surface. That's exactly what we're doing here. Now, once you understand this, then the rest is just substitution. So I could just do W transpose in both the sides. W transpose X is equal to W transpose, let's just call this as, I don't know, X orthogonal plus R W transpose W by W, right? So all I have done here is added a W multiplied by W, all the terms, right? So now I could also add plus W0 in both the sides. So this becomes W transpose X plus W0 is equal to W transpose X bar plus W0 plus R times W transpose W by W. Okay. Now what is this? This is essentially Y of X is equal to, what is this? This is essentially X bar plus R times W transpose W by W, right? So now y of x is equal to, now x bar, remember that x bar actually lies in the decision surface, so it is 0, right? So this is equal to 0 plus r times w. Okay, so now from this you can find that r is equal to y of x divided by w. Okay, now what does this mean? This means that the length of, let's go to the same picture. So this length, right, is essentially y of x by w. Or in other words, when I take any random x and compute y of x tells me the orthogonal distance of this point from the decision surface. Now, by just looking at the sign of this function, you could say whether it is this much distance in the top or from the bottom. Okay, so the third observation is essentially the signed orthogonal distance of a general point x from the decision surface is given by y of x divided by w. Okay, so I think that's mostly the three observations that like we have from these linear discriminant functions. Okay, so maybe I would summarize this once before we will just stop with this, but I'll just summarize what we have learned about linear decision surfaces. Okay, so we will just go with pictures. So I have x1 and x2. So this is two features that I have. Okay, and let's say this is my decision surface. Y is equal to 0. Anything lying above, like y greater than 0, belongs to class 1, and anything which lies below this belongs to class 2. Okay, so we had three observations for a simple model, which is y of x is equal to w transpose x plus w0. So what is our, okay, so there are three terms here, right? Like, so w, w0, y of x, right? So every term has some interpretation. So that what is w? W determines the orientation of this decision function. So essentially, maybe another way to put this is, let's say we don't have, okay, I cannot erase this. Okay, it's okay. So essentially, if my W is like this, then my decision surface is orthogonal to W, right? So if you look at the angle between W and the decision surface, it's 90 degree, right? So W determines the orientation. So W determines the orientation. Okay, so then we have W0. What is the role of this bias? The role of this bias is it determines this distance. Okay, this distance is given by minus W0 by W. Okay, so W0, it determines the displacement of the decision surface. Is that clear? Okay, so finally we have y of x. To understand what is y of x doing, we could take any random point, let's say this point. Now, this is my vector x, right? I could divide this vector into two parts, right? So, right? So now this is 90 degree, and let's just call this as x bar. So now this line is x bar. And what is this line? So we don't know what is this line, but we know that this line is exactly some rescaling of W0. It's in the same direction, sorry, W. It's in the same direction as W, right? So in some sense, this line, right, is R times W. And we found that this R is essentially y of x by W, right? Or in other words, the term y of x, it tells you like the signed orthogonal distance, like from the decision surface, right? Like so by just looking at the sign, you should be able to say which part of the decision surface you are in, and by looking at the magnitude, you should be able to say how far is this point from the decision surface. Okay, I think that summarizes like today's lecture. So we did a lot of geometry today, but we will see how to use this understanding in designing algorithms from the next lecture. Okay, so I think that well, we are running out of time. So that technically is the end of the lecture. I would probably take one or two questions and then stop the recording and then maybe take more questions. Okay, so is there any question in the chat that I should answer?
There is no question in the chat.
Okay.
There is one raised hand.
Yeah, Masoud, you could speak now.
Sorry, so technically you decompose any vector in R two-dimensional into two new biases. I mean, X,
we are not
X orthogonal and RW. Any vector with respect to these two.
Oh, well, like, so here we are decomposing it just to understand the, like what y of x means, right? So I'm decomposing x into x dash plus RW so that we understand that y of x gives you the distance from the decision function. So the x is the sum of these two different vectors. Okay, okay, I think there are a couple of other raised hands. Yeah.
Gabriel.
There are a couple of raised hands.
Gabriel, you can speak.
Okay, you hear me now?
Yeah.
Okay, I muted my microphone. So my question is, if you were to multiply the weights and the bias by a constant factor, let's say beta or alpha or something, then you would have the same decision boundary. So your solution is kind of degenerate if you were to try to optimize a loss function to have a solution. Some problem.
Okay, can you repeat your
basically question? Let's say you have an optimization problem, you want to separate two classes.
Okay, I think I get your point. Well, like if you're multiplying both by a specific factor, then you might not be solving the problem, right? Like, because in some sense, I was just showing the boundary here, but there is also data, right? So for example, let's say this is my data. Okay. If you're scaling these two things, then you're essentially shifting the decision boundary. So like you cannot scale it to as much as you want.
But if you scale the W and the W0, then you would have the same decision boundary because it's equal to 0 that defines the boundary itself. Like
okay.
you have a learning algorithm that gives you W equals to vector 1, 1 and W0 equal to 2. Then if you were to just multiply your solutions by 5, then you would have exactly the same decision boundary.
Okay, so okay, I need to think about it. Like, so maybe I will stay in the call so that I can think a bit and answer for that.
Okay, well, thank you.
Okay, so I will stop the recording.